delta x and then our delta t, distance and time, and we just say delta x divided by delta t, bam, that's our velocity. You know, so we have to make these measurements. But maybe if there's some weird way of being able to fiddle around with both of these numbers, maybe that would explain why, because, so this guy, I'm doing this measurement, this guy is doing its own measurement. For him, it's just going from the beginning of the train over here, and so he's making his own delta x, delta t measurement. And if we can play around with how we're perceiving our space and our time, it's just such a weird way of trying to go about it, but like, okay, fine, mathematically, I guess that's an act. That's one way that I can trick myself into thinking that we're both measuring the same velocity at the speed of light here. So then the other two, I'm not going to call these, no, so I'm going to get rid of these guys because we happen to know that the speed of light is not infinitely fast. In fact, it's about 3 times 10 to the 8th meters per second. It's real fast, but it's not infinitely fast. So the other two things I'm going to present as axioms, and I'm going to then go on to the wrapping a little bit.
There's an eraser down there.
On your right. Right there.
No, just the chalk eraser.
Oh, I'm fine. Length, contraction, and time dilation. Length contraction, let me make sure I get these relative quantities right here, can be simplified by a proportional statement. L, the distance that I measure for my delta x, is going to be equal to L prime, the distance that the dude in the train measures, delta x prime, divided by some factor. And this factor is where all the magic of special relativity comes from. If it weren't for this factor, then ultimately, I don't know, maybe this isn't the cleanest example, but ultimately, this is a factor which plays around with our relative sense of distance, of measuring distance, and our ability to agree on how any kind of distance, how far something is. Time dilation is described by a very similar equation. T, like the length of time that I would measure, is equal to the exact same gamma factor times t prime, which is the length of time that you measure. And this is it. That's it. That solves our problem, right? We plug in these fudge factors into our relative measurements of dx dt, and ta-da, speed of light is the same. Aren't you all happy and satisfied? Now we know special relativity.
It doesn't make any sense.
What? So this gamma factor here, and this isn't gonna, this is just, this whole lecture is the explanation, by the way. So, but this gamma factor here, and I'm not gonna get into real details about this. Here, let me use a little more space here and I'll get rid of this. Gamma is defined to be, don't bother writing this down, but 1 over the square root of 1 minus v squared over the speed of light squared. So c is the speed of light, just sometimes I'll make write that out there. And v is the relative velocity between me and the train. And this is exactly what we're talking about here. So this function behaves a certain way. This is a function of velocity alone, of our relative velocity between me and the train. If the velocity is 0, 1 minus 0 is 1. The square root of 1 is 1. 1 divided by 1.
1.
My gamma is 1. So if this is v, and this is gamma, when v is 0, gamma is 1. Alternatively, when my v becomes very, very, very close to the speed of light, because you never quite reach the speed of light, but you can get as close as you want, this becomes very, very, very close to 1, a little bit smaller. 1 minus that is a very small number. The square root of that is also a very small number. 1 divided by a very small number is a very big number. And that's all we're going to do for that kind of analysis, but it ends up being a very sharp peak like this, and then it goes up to infinity at e equals the speed of light. We're not going to get any more detail into that, but that's what gamma is. It's worth saying because I'm going to throw gammas around a lot here, and that's what it is. So it's worth noting, though, this is really flat towards the beginning. You have to go really fast in order to get some meat out of what this gamma factor is to play around with these things. And that's unfortunate, because that means we don't get to see these crazy effects in our daily life. And I would love to see them because they were so cool to read about. But we don't get that. We just get ordinary Galilean relativity in our daily lives because it's so close to 1 all the time. So, let's see here. Yeah. So the next topic, which is going to be the whole topic I'm going to talk about today, this is the way in which I like to introduce special relativity. There are many ways in which people like to go about this topic. It's such a phenomenal topic, and everyone loves it. But I like to do it with paradoxes, because I think it's extremely natural to find paradoxes when you're talking about this, because it doesn't make any sense. And that's good. That feeling of not making any sense is exactly what I'm trying to capitalize on. Because if you can define a scenario which just isolates the quantity, which like exactly what doesn't make sense to you, and then resolve it, you've just totally conquered that little bit of it. And there's more than one to special relativity. But, so the paradox we're going to talk about today is the barn and ladder paradox. And everything I talk about today is going to be in reference to this guy. So, actually, I probably should have stated one more final bit about what I mean by length contraction and time dilation, rather than just them being some kind of convenient fudge factors. So, specifically, the statement is that length contraction, look at this guy. Length contraction means that if you're moving relative to me, you're skinnier. To me, maybe that's one way of phrasing it. But if one of you were to get up in front of this room and run really, really fast next to me, and I had the world's best measurement of your length, I would measure, oh hey, you've lost a few pounds. You're literally, you're squished. And if you're really close to the speed of light, you're like a pancake. So it's not a compliment. That's actually only around the direction that you travel to, just as a matter of course. But, so that's what length contraction is. It's the idea that if you're moving relative to me, then you're skinnier to me. And it works both ways, because we're talking about relativity. So if you're running, according to you, you're just doing this weird motion, and I'm flying backwards, if that makes sense. And so, according to you, I'm the one that's looking skinnier, and you're just normal. Because when you're standing still, you look normal, and your time moves at a normal rate. That's what it means to be you. You know, in your frame of reference, you're always just being you. And everyone else is going all crazy and getting skinnier and time getting all messed up, but you're always normal.
Yeah. So I can go on a diet by watching people run.
You got to get them to run in order to if they want them to see you as being skinnier.
That's why
we're physicists. We're smart like that. And then time dilation is the other guy. It's the temporal side of things. This statement means that if you're, once again, if you're running next to me super, super fast, and if I look at your watch, or if you're trying to talk to me, if I see you doing something in time, I will think you're doing it in the slow-mo version of time, even though you're flying by me.
So that's my solution.
That's your solution.
Okay.
If you're flying, actually, do I have an example of someone who wants to get up here and wants to just run back and forth a lot? It sounds like a lot of fun. That's all right. It's not really worth it. But if you're running, if I'm going to run, I'll just do it. So you're all standing here. I'm going to run. And so, that's the idea. All that to sink into your mind. But that's the time dilation. And just like in the length contraction case, it's all a matter of perspective. It's all relative. For me, when I'm doing my little Jim Carrey routine here, I see you guys as doing ho, ho, ho. And you're all squished together a little bit. It's all a matter of